Welcome to the shape of molecules. All right, so now we're going to talk about the shape of molecules and what that means. So find this little section in your notes and let's get going. First off, we're going to look at the notes. It says the shape of a molecule describes the way in which its atoms are arranged. So you might look like this, you might look like this. I know that's a black atom in the middle. You might look like this. Now, all of these, all of these are different shapes of molecules. And we're going to explain why each one of these shapes happens. Here's another one. Sorry, there's another one that's just nice and flat through there. Okay, so why do these shapes happen? So the shape of a molecule describes the way in which the atoms are arranged. For example, hydrogen or H2, here we go, and hydrogen fluoride. Oh, sorry, I can't get everything working all at the same time. Here we go. So hydrogen and hydrogen fluoride are what we call linear. Yeah, you look at them, they just, whichever angle you look at them, they look like they are just a straight line. Okay, so they are linear molecules. Both atoms must form a straight line. However, when we have more than two atoms, there are a few more possibilities. In fact, there are 5 different shapes that you need to know about, but 6 different combinations. So 2 of them have the same shape name, but the rest of them are different. They all have a different reason as to why they occur. So the thing here is that all electrons, so in the second paragraph, all electrons are going to play a role in the shape of the molecule. Every pair of electrons wants to be as far away as another pair of electrons. Okay, so this is saying even non-bonding pairs, even your lone pairs, are going to repel each other. And this is according to the VSEPR, or valence shell electron pair repulsion theory. That was lucky. In the diagram here, you can see it shows how many atoms are around the central atom. It doesn't tell you the number of bonds, but it just tells you how many atoms and how many lone pairs there are. And therefore, what is the name of the shape and why is it arranged that way? Okay, so let's go through each one. Yeah, well, let's finish this. So it says, however, underneath the picture or on the next page, it says, however, the name of the shape of the molecule is given to describe the shape that the bonding electrons make. Okay, so the name is coming from bonding electrons only. Okay, so that's what gives us its name. Now, I'll go through that in a second. So overall, all the electron pairs create the arrangement, but only the bonded pairs contribute to the name of the molecule. Okay. We'll come back to that example on the next page. So let's just have a look at our first example. So the centralized molecule that we're looking at here, the central molecule, that one is going to be my black carbon here. Okay, so my black carbon molecule in the middle. Yeah, and this is carbon dioxide. It's got an oxygen over here, it's got an oxygen over here. And can you see that there are no lone pairs? There are no flat sections on this oxygen. There are no flat sections on this oxygen. You can see that there are 2 bonds, even though they're double bonds, but they're 2 bonds, one here and one here that's coming off my central atom. So that's what puts us in this group here. Hang on. That's what puts us in this group here. Now this shape is obviously linear. Yeah, it's not quite as small and compact as this linear molecule, but you can see that it's still a straight line. Okay, so that's my linear lone pair. So my linear molecule that is one central atom surrounded by 2 other atoms, and that will form a linear one. And that's because we want 180 degrees between both sides. So whichever way you go, we want to make sure our electrons are repulsed by at least 180 degrees, or so by 180 degrees. So let's go down and we'll say one central atom surrounded by, sorry, let's find the right one. One central atom surrounded by, let's turn around that way, surrounded by 3 other atoms, no lone pairs. Okay, so what do they want to do? They want to be as far apart from each other as possible. Now, I couldn't actually model this very well with my kit, but I've done my best. So what happens is they form along the same plane. Yeah, can you see how all of them are in the same kind of flat plane here? Yeah, but they are all equal distance apart when you look on the side or look at it from the front there. So this shape here with 0 lone pairs, that's called a trigonal planar. Trigonal because it's got 3, yeah, like a triangle, and planar because it's flat. It's a straight line like this. Okay, so that's that one. Now, what would happen if that lone pair existed? Yeah, so if you've got a lone pair there, what you're going to end up with is something that looks a bit like this. Okay, can you see how this is different to this one? It's a bit of a subtle difference. But can you see how all of the hydrogens in this molecule down here, they're all kind of down the bottom? Yeah, all of those hydrogens are down the bottom. And that's because this up here, this little blob of blue tack, that's representing my lone pair. And that lone pair is going to repel all of those hydrogens and all of the electrons that those hydrogens have. And it's going to kind of push them a bit further away. Now, it can't push them all the way around the other side of that central blue atom, but it can push them down a little bit more. And so this actually, oh, sorry, I've gone down to my 4 here. So I just jumped around a little bit. This one is a bit different because this one is actually got 4 potential bonds here. So 4 potential atoms coming off. So 1, 2, 3, 4. There's the 4th one coming off there. And this one up here is my lone pair. And you can see why they're all pushed apart. And this is actually called a trigonal pyramid. So you've got to think, are there 3 atoms with no lone pairs, or are there 3 atoms with a lone pair? Once you put in the lone pair, that's going to push those other atoms down a little bit and make it trigonal pyramidal versus trigonal planar. And that's probably the most difficult ones to understand. The last 2 are a lot more commonplace and good for us to discuss. So we have 3, 1. So I'm going to go here. We're going to talk about why this one is bent. So this is a molecule here. This is what it looks like, but it has a lone pair up the top here. So this is something that could form 3 bonds, but normally it would be straight. Yeah, it would be linear if you had 2 atoms. But if you tried to make that linear, look at how close the lone pair is to that one. It doesn't like it. So it moves itself around a bit, and we end up with this bent shape. So even though this lone pair is here, we call this shape bent because it is definitely bendy in the middle. So that one there is my 3 molecules and 1 lone pair. I'm going to leave the tetrahedral to last. I'm going to show you the other bent because it's very similar. So here is our other bent molecule. This one has got 2 atoms bound to it and 2 lone pairs. So that's the difference here. This one has 2 atoms bound to it and 1 lone pair. So there we go. But they both end up the same shape. Now, if you look at how far apart they are, we already told you about this one. With this one, it's a bit more 3-dimensional. So you can see there's these 2, they're about as far apart as they can be from these 2 down the bottom here. Okay, so it's just all about as far away as possible from each other. But even though this one has 2 lone pairs and this one has 1, if you only bond to 2 things, but you've got some lone pairs, you are going to be a bent shape. Now, the very last one is my favorite. This one's called tetrahedral. Tetra, meaning 4. That's this guy here. That's like your classic look at me molecule. So when you talk about molecules in a 3-dimensional space, you have, here's my central atom, and every one of those outside atoms, if you measured this angle, if you measured this angle, this angle, this angle, this angle, you would find they're all the same, and they're all 109 degrees. So the fact that they're all the same means that we're as far apart from each other as we can get, while also maintaining a shape. And what that shape is that we end up with, that shape is called tetrahedral. And that is the end of my introduction to the shape of molecules.